Okay.
Yeah, I have like all the signals that I can pull from our side, but now I have to go to the other side, which is less fun. But, well, I mean, just this isn't going to be here before it starts.
I had to, we were talking about Gauss-Newton's method. Before we talk about Gauss-Newton's method, I wanted to make an important announcement. So I will be on official travel on Wednesday, Friday, and next week Wednesday. So there'll be no classes this Wednesday, this Friday, and then next week Wednesday. So what I want you to do during this time is to spend some time thinking about what project you want to do, and of course the the topic for the project is due next week, I think. So you will have to write down whatever topic you want to spend your time doing the project on. One of the things that I mentioned in the course information sheet, and I'll mention it in the class as well. Ideally, you want to pick a topic for the project, for the optimization project. You want to pick a topic that is based on an industry that you are targeting, and it should be solving some concurrent problem of that industry. So if you're interested in logistics, you should try and pick up a optimization problem in logistics. If you want to get a job in Google, you should try and pick a problem that is of interest to Google. One of the ways to know what is of interest to Google or logistics companies is to look at their recent postings on LinkedIn, looked at their recent postings or the job postings. They'll mention what topics they want the person to solve, and based out of that, you can figure out a specific topic that you would like to study for your optimization project. Generally speaking, I know that there are a lot of undergrads in this class. So generally speaking, whatever you do in the project, you can definitely upload the code on your GitHub repository. And then whenever you are going to talk to a potential employer, specifically from the industry that you are targeting, you can direct them to your GitHub link. You can direct them to your project report. You can direct them. You can write that in your CV or in your resume. So it's just going to help you find a better job, and the project will help you get the foot in the door for that particular industry. I don't have any specific requirements on the project topic, but definitely you will have to spend some time writing the code or reading the paper. So if you're a PhD student working in a research area, you want to spend some time reading papers in that area, and then hopefully write that up in the project topic. If you are an undergrad and you are targeting some industry, you should probably solve an optimization problem from that industry, and submit the code and a project report as part of your submission. Any questions on this? No classes on Wednesday, Friday, and next Wednesday. Any questions on the project topic? No? Yes.
So for the classes, will you just like pull all the lectures that we'll use, or will we like pick up when you visit that?
No, whenever I'm back, I don't want to post lectures on YouTube. Okay. Any other question? Yes.
Did you say you're going to be here next Monday? Because
I will be here next Monday.
Okay.
Yeah. So I'm going to 2 separate conferences. So that's why. Yeah, one conference this week, one conference next week. Okay. Yeah, so we were talking about Gauss-Newton's method. Our problem statement was, I want to minimize x in Rn, half of norm of gx square, which is summation I equals 1 to m gix square, and this is my function f of x. One of the things we mentioned in the previous class was gradient of the function f of x is gradient of g of x, gradient of g of x transpose. So this is n cross n. No, sorry, this is the first derivative, right? So first derivative is not there. It's gradient of g of x times g of x. This is in Rn. So if you recall, this is a matrix in n cross m. This is a matrix m cross 1. So you get a vector in Rn, and then the second derivative of the function is gradient g of x gradient gx transpose plus summation I equals 1 to m gix second derivative of gix. Okay, so this is what we did in the previous lecture. This is where we stopped. And one of the questions that I had asked you is, if you were to solve this problem and you want to benefit from Newton's method, but you don't want to have the additional complexity of Newton's method, what are you going to do to solve this problem? Again, our objective is, I love Newton's method because it's very fast, it converges to the optimal solution very quickly, and by an appropriate choice of step size. But Newton's method is also complex, and I don't want that complexity of computing complicated derivatives. Okay, so if this is the problem, what would you do? Yes.
You use x0 instead of just x. Like,
So compute the second derivative at time 0, and then after that just use it all the time. Is that what you're suggesting?
yeah.
Okay, we can do that for sure. Anything else that comes to your mind? So option 1, compute second derivative of fx0 inverse and use all the time. Anything else? That is definitely one of the, oh, did I write compute? Anything else that you guys want to contribute to? No? Okay, so one thing that you recognize, let's try to look at these expressions somewhat carefully. So okay, so suppose so every time, so in order to use gradient descent, I have to compute the gradient of f at every point of time. In other words, I have to compute the gradient of g and evaluate this function g of x at every point of time. Now let's look at the second derivative of the function. I have gradient g transpose. So this is something that I've already computed because it's required for computation of the gradient of fx. But then I have this particular term which has the second derivative term, and there are m such second derivative terms. So this is a matrix that I've already computed based on the information that I have. Computation of gradient is complicated, but is matrix transpose a complicated operation? It's not really a complicated operation because all you're doing is multiplying a bunch of vectors, right? So vector multiplication is not complicated, and especially in the age of GPUs are actually optimized for vector calculations. Okay, so vector multiplication is not a problem. Computing this, not a problem, because we already have the gradient computed in order to compute the gradient of f of x, and this is the term that is complicated to compute. So let's try to ignore it. I'm going to ignore this computation. I have a symmetric matrix. Perhaps it is positive definite. So I have a symmetric matrix. Probably it is a positive definite matrix. If it's a positive definite matrix, I will pick in the Gauss-Newton's method I'm going to pick dk to be gradient gxk transpose inverse. Now if it is not positive definite, then I'm going to pick dk equals to same thing, plus some positive definite matrix. So pick any positive definite matrix, whatever is your favorite positive definite matrix, identity matrix, some multiple of identity matrix, or something else. So you keep the same thing, you keep this term here, you add a positive definite matrix so that this entire thing becomes a positive definite matrix, then you take the inverse. Okay, so this you add the term so that this whole thing is a positive definite. So by the way, this could be, it's definitely not negative. It wouldn't have a negative eigenvalue, but it could have zero eigenvalue. Okay, especially when you're getting close to the optimal solution, this gradient is going to vanish. Okay, or alternatively, this g of x is going to vanish. So one of these two terms is going to vanish because the gradient of the function f has to vanish when it's converging to the optimal solution or to a stationary point. So this thing has to go to 0. So either this thing will go to 0 or this thing will go to 0. And and if this thing is going to 0, then this term could be positive semi-definite, which means that it might have some 0 eigenvalues or close to 0 eigenvalues. So what happens when you have close to 0 eigenvalues? Let's think about it. So I have, let's say my positive definite matrix is 10 raised to minus 3i, and I want to invert it. What's the inverse of this particular matrix? Okay, so I have the identity matrix, I'm multiplying it by 10 raised to minus 3. What's the inverse? 10 raised to 3i, right? So if the eigenvalue of the matrix is going to 0, the inverse is going to have very large eigenvalues. If this has large eigenvalues and I'm going to multiply it to the gradient of a function, the gradient of the function will become very big. Okay, we want to avoid those situations, as a result of which, if the eigenvalue of this is going to 0, I'm going to add a positive definite matrix, my favorite positive definite matrix, just an identity matrix or some multiple of identity. You can figure out what the best matrix is through trial and error, after which you can use that matrix, invert this whole thing, and then run the Gauss-Newton's method, wherein we've ignored the second order term and only kept this particular thing. So it gives you an idea of how to design algorithms. Typically, when we are designing algorithms for optimization, if we are already computing something, we want to make maximum use of that information. And as long as we can do some matrix multiplication, matrix manipulation, we just want to make use of the information we are already computing in order to speed up the convergence, instead of trying to compute complicated second derivatives or higher order derivatives and use that for solving the problem. This type of problem appears quite frequently in training neural networks or training machine learning models. Okay, so I don't know how many of you are going to use the course project to do something in machine learning, but typically in machine learning, this is the kind of problem you will be encountering. And towards the later half of the course, maybe in mid-November, we'll talk about training neural networks in the class using dynamic optimization, and we will encounter this specific problem at that point of time. Yes?
Can we have a step-dependent delta K?
Can you have a?
Step-dependent, like a variant.
Yeah, so that's why I have delta K. So you can have like, in the beginning, you can have like 0, like delta K is just 0, right? Because this term is going to be large, so this is going to be a positive definite matrix, so you're good. Towards the later half, as this term is going to 0, you can start increasing the value of delta K. Okay. Any other question? Okay. By the way, I still haven't figured out, I didn't get the chance to figure out why it's called Gauss-Newton's method. What does Newton have to do with all this method? I haven't figured it out, but hopefully one day I'll figure it out. Okay, any other question? Let's talk about the next method, which is conjugate direction method. Anybody from physics here? Physics? No? Chemistry? No? Okay. So this is a problem that appears in physics or chemistry. I want to minimize x in Rn, half of x transpose qx minus b transpose x. So this is my function f of x. Q is a positive definite matrix, b is a vector in Rn. So if you want to work in nuclear fusion kind of industry, this is a problem you would encounter. In nuclear fusion, high energy physics, particle physics, and molecular dynamics. Okay, so I have this problem statement. I want to minimize this function. What's the gradient of the function? So this actually is a convex function. So let's look at it. What is the first derivative of the function? That would be qx minus b. What's the second derivative of the function? That is q, which is a positive definite matrix. So it's a convex function. So f is convex. So gradient f of x star equals to 0, which means x star equals to q inverse b. So because f is convex, first order necessary condition is also sufficient. X star is optimal if and only if the first derivative is equal to 0. I set the first derivative equal to 0, I get x star equals to q inverse b, and that is the optimal solution to this minimization problem. We can actually compute it by hand. Why do we have to come up with a method to solve this problem? What is complicated about this expression? If I'm given the matrix Q and I'm given the matrix B, why can't I just be done with the problem by doing Q inverse multiplied by B? Yes?
Maybe that would be, what if the matrix is like a million or a billion?
Yeah. So this is difficult to do when Q is a billion cross billion dimensional matrix. You can't even store it in your memory. In fact, you can do this experiment at home. It takes less than 5 seconds to do it. You can fire up your MATLAB or Python or whatever is your favorite programming language. Create a matrix. Just use random matrix, rand 10 raised to 3, 10 raised to 3 inverse. Just compute this, and your computer is almost surely going to crash. Just with 10 raised to 3. Okay, so I'm just talking about 1000 cross 1000 matrix. So I pick a 1000 cross 1000 matrix and I want to invert it in today's computer, like today's laptop. So it's a sophisticated machine, right? So you probably would have 16 GB or 24 GB or 32 GB of RAM. And depending on how many GBs of RAM you have, You can make it 10 raised to 3 or you can make it 10 raised to 4 and your computer is going to crash. Okay, now imagine if this Q was a billion cross billion, as is the case in high energy physics, as is the case in nuclear fusion, and as is the case in molecular dynamic simulation. Okay, so in molecular dynamic simulations, they want to simulate how atoms are interacting with each other. Okay, so somehow this Q and B, I don't know much about it, so I've just read a bunch of papers. Not a bunch of papers, I just read the introduction of the paper. So basically, some sort of energy function is contained in this matrix Q and some sort of interaction functions are contained in this matrix B. And this is the kind of optimization problem you get. And as is the case, the number of particles would be of the order of a billion, right? So even this chalk would contain a billion or more atoms. So this will become a very complicated matrix, and now we need to solve this X star. We need to compute this X star. So for that, people came up with conjugate direction method. I think late 1960s is when they started looking into it. Why were people looking into these problems in late 1960s? So I don't know if I'm sure you must be aware, there was a lot of talk about Cold War and nuclear attacks on each others and whatnot. And so people, physicists who were studying nuclear physics were actually trying to solve problems of this type. So a lot of the stuff that we study in optimization, it was developed during World War II and during the Cold War for war purposes, okay, to optimize something, so optimize the movement of troops, optimize the supply chain, optimize the global shipping, optimize the warhead, all kinds of bloodthirsty reasons for which these optimization problems were designed. Anyways, so we are studying algorithms that were designed for winning the war, but of course they are useful for other things nowadays. Okay, so the question is, I want to solve this problem and I want to come up with a method that solves this problem either exactly or approximately in certain number of steps. Yeah.
I think there's something called like a pseudo inverse. Is that gonna help?
No, pseudo inverse also takes a lot of computation. Okay. And the other thing to recognize here is I'm not interested in Q inverse. I'm interested in multiplication of Q inverse and B. So if without computing Q inverse, I can compute Q inverse times B, that is even better. Okay. So even if you want to do pseudo inverse, you still have to invert this matrix. And pseudo inverse is typically useful for matrices with 0 eigenvalues, which are not invertible. So then you do pseudo inverse. So this is positive definite by assumption. Okay. So the goal in today's class is to talk about how do I compute Q inverse times B. I don't even have to invert the matrix, right? Because all I'm interested in Q inverse B. So let's try to figure out how to compute this. Okay. So you did one assignment problem in your assignment 1, which is Q conjugate vectors. So you have D1 to Dn are Q, or D0 to Dn minus 1. Well, D1 to Dn. Maybe I'll start with X. No, I want to start with X0. I don't want to start with X1. Yes. I think I should have D0 to Dn minus 1. Q conjugate if di transpose Q dj equals to 0 for all I not equal to j. So what I'm going to do is I'm going to come up with these Q conjugate vectors D0 to Dn minus 1. So right now we'll talk a little bit in hypothetical. So let's say God came in my dreams and gave me d0 to dn minus 1 for this 1 billion cross 1 billion matrix. So I have the Q conjugate vectors in my arsenal, and I'm going to run the iteration xk plus 1 equals to xk plus alpha k dk, and alpha k is equal to arg min of alpha in R. So remember, the step size could be negative in this algorithm. So alpha is in R, f of xk plus alpha dk. That's my algorithm. I don't need positive step size, so my step size could be negative, but I'm using the minimization rule to compute the step size, and dk is something that's given to me by someone. Okay, so let's try to compute. So there are two questions here. The first question is, how do I get to these Q conjugate vectors? So that's question number 1. Question number 2 is, what's this value of alpha k? So let's try to find the value of alpha k. So this function f is convex, right? So f is convex, so f is also so f is convex in x. Alpha is appearing here, so f is also dk is given already. So f is also convex in alpha. So all I have to do is set the first derivative equal to 0 and get the value of alpha k. So let's see what the first derivative is. So question number 1 is, alpha k equals to what? So let's try to solve it. So gradient of del over del alpha. I have to solve this equation. So this is given by dk transpose what is the value here? That would be let me write it as dk transpose gradient of fxk with a negative sign over dk transpose dk. Okay, so I'm taking the derivative with respect to alpha, assuming xk and dk is given, I'm setting it equal to 0 because I want to find out what alpha k is. And so alpha k is going to be given by this expression. Okay, so if you look at the expression closely, the gradient of fxk appears here. This is something I have to compute anyways because it's a gradient method, so I have to compute the gradient. And dk is given to me by God or by CIA or by the President of the United States. So dk is given to me. And here it's dk transpose dk, matrix multiplication, easy peasy, matrix multiplication, easy peasy. So this entire thing is easy to compute. Yes.
Is that like a negative or did he just?
There is a negative sign. So qxk minus b is the gradient. So this is negative of gradient, so I took the negative sign in front. Okay. So what I'm doing at every point of time, I'm standing at xk. I have this direction dk. Minus dk. So I'm looking at this line. So I'm standing at xk. I'm looking at two directions, dk and negative dk. So I'm looking at two directions and I'm picking the value of alpha such that the function is minimized along this particular line. Okay, that's what I'm trying to do. I'm taking the argument of the function along this line xk plus alpha dk for values of alpha in R. So I could have a solution in the positive direction or I could have a solution in the negative direction. So I'm looking at this entire line, picking wherever the argument is, and that becomes my xk plus 1. And then I'm going to pick another dk, like dk plus 1. Let's say it's in this direction. So this is dk plus 1, and this is negative dk plus 1. And I'm going to pick alpha k plus 1, and this will be my xk plus 2. And I'll keep repeating this process again and again. Okay, so starting from xk, I go to xk plus 1. And then starting from xk plus 1, I look at the direction dk plus 1 and negative dk plus 1. And I pick alpha k plus 1, and that gets me to xk plus 2. Yes?
How are we going to pick the dk?
Right, so now the question number 2 is how do we pick dk? Okay, so question number 1 was how do we pick alpha k? Question number 2 is how do we pick dk? Question number 1 is answered. Okay, and this is what the pictorial description of what is happening in the algorithm. So now let's go to question number 2. How do we compute Q conjugate vectors? Now this is something that was your assignment problem, so I assume everybody, although I know a few people have not submitted their assignment, I don't know why they have not submitted it, but I'm assuming that you know about this Q conjugate vectors because it's something that was part of the assignments. Okay. Again, I want you to think about if you were to encounter this problem, how would you go about coming up with Q conjugate vectors? What would you do? So I'm given a bunch of vectors, C0 and Cn minus 1. I can compute Q conjugate vectors by setting D0 to be C0 and D k plus 1 equals to D0 plus summation j equals to 1 to k c k plus 1 j dj. Is it dj or, oh no, sorry, not d0. Yeah, So d1 will be c1 plus some scalar multiplied by the previous directions that you have picked. So can someone, if you have the assignment solution, can someone tell me what c k plus 1j is equal to? If you have done the assignment, then you might have the expression. No, q. This is for all 0 less than equal to j less than equal to k. Okay, so this was the assignment problem. Now let's see if ck plus 1j is easy to compute. So I'm given these vectors. These vectors are given to me. I can generate these vectors on the fly. I can just use a random vector generator like a function like rand or randn. And I can generate these vectors on the fly. And then this is the way to compute the q conjugate vectors, where dk plus 1 will be the random vector that I have generated plus the summation of all the previous vectors that I have generated so far, where the coefficients are given by this expression. The coefficients are easy to compute because this is matrix multiplication, this is matrix multiplication. So even if I have a billion cross billion matrix, I want to multiply it by vector, I can do it somewhat easily with multiple processors and multiple high bandwidth connection between servers, and I can still be able to execute this kind of computation. So it's possible, it's feasible to do it. So this is easy to compute. Okay. Now the question is, can we simplify further? So far, the question was, how do we compute the q conjugate vectors and how do we compute alpha k? So alpha k turns out to be an easy thing to do. And q conjugate vector also turns out to be easy thing to do, easy to compute. So I'll be able to do both these things. But can we simplify further? Okay. And so where would the simplification come from? Yeah.
QBJ is again in the denominators.
Sorry, can you say that again?
So the QBJ is both in the numerator and in the denominator.
Right. So this is something that you are computing in the numerator and denominator, so you can store it in the memory, and therefore you don't have to do that multiplication again and again. So very good. That's one way to simplify the computation. What else can we do? Okay, so his suggestion is, this is something that's getting computed, by the way, not just in the numerator and denominator, but you have to do it every time you compute a new q conjugate vector. So definitely something that you can store in the memory, and of course the memory complexity increases. So another thing that you need to remember, when you're solving an optimization problem, you can have computational cost, you can also have a memory cost. You might need a larger, like let's say now you are storing this in the memory. This is a billion dimensional vector. So now you have to store that billion dimensional vector somewhere. So you need to have that memory available to you. But good point. This is something I can compute, pre-compute and store in my memory, and then keep using that from the memory itself. What else can I do? Okay, so one thing that I can do is I can define my ck to be gradient of fxk, or maybe negative of the gradient. Negative of the gradient. I have to compute the gradient anyways. Remember that the gradient is being used here. So I'm going to let Ck be the negative of the gradient of the function fxk, and then it simplifies, things simplify. So in this case, so if Ck equals to minus gradient of fxk, then we have d0 equals to minus gradient of fx0, and dk equals to minus gradient of fxk plus beta k dk minus 1, and beta k is given by minus gradient fxk transpose minus gradient fxk. Okay, so this is a general method where you can compute Q conjugate vectors using arbitrary vectors, but you can simplify it even further by just picking the vectors, this original vectors, to be the negative of the gradient, after which the computation of dk Q conjugate vector simplifies. So this is the way you compute Q conjugate vectors, this is the way you compute alpha k, and then you run the algorithm in this particular fashion. And now you don't have to compute matrix inverse at all. And this method is guaranteed to converge to the optimal solution in n time steps. So you can get to the optimal solution much earlier, get closer to the optimal solution much earlier, so you can choose to kind of not compute further. You can choose to not go through further iterations if you think that your gradient of f is close to 0, right? So typically the termination criteria in all gradient method is, if my gradient is below a threshold, I'm just going to quit. I'm going to say I'm close to the optimal. I don't care about running it for infinite iterations. I'll just quit. So let's say you have a billion dimensional vector here, and this is a billion cross billion matrix, and you're applying this algorithm, and after a million steps, you realize that the gradient of f at x 1 million is, I don't know, 10 raised to minus 3. You can say I'm done. I don't have to go all the way to the billion steps in order to compute the optimal solution. I'm happy enough with x 1 million. So you can get to the solution much faster, or at least an approximate solution much faster, with the conjugate direction method. Any questions so far? Yes.
Is this guaranteed to go to the literal solution?
Yes, so it's guaranteed. I'll write the guarantee. Guaranteed to converge to x star in n steps. So if you have a billion, if x is a billion dimensional, then you will take a billion steps to converge to x star.
Does that mean for smaller matrix, it's actually better to use this because it's...
Yes, I think in the current assignment, you have to do it for a million cross million matrix. Sorry, not a million cross million, 1000 cross 1000. Okay. So n is 1000, and you will see the convergence to x star in n steps. But remember that even for your computer, inverting a 1000 cross 1000 matrix is difficult. Okay, I'm assuming for most of you, the computers will sort of give up at 1000 cross 1000 matrix inverse. But you will be able to solve this problem in a few seconds, 2-3 seconds. You should be able to solve this problem and get to an optimal solution. This is the way to generate Q conjugate vectors. This is the way to generate alpha k. So something you thought was impossible will be possible using conjugate direction method. Any question? Now what if this function f of x is not quite a quadratic function? So this is the quadratic function, this is the quadratic term here. So let's say your f of x has some non-quadratic terms as well. So it's kind of a nonlinear function, but it's kind of sort of behaves like a quadratic function. Then what do? So it turns out that the algorithm remains somewhat similar, except that of course this will no longer be alpha k. So remember, the alpha k actually required you to set this equal to 0. So if f is convex and you go through this process, then alpha k is given by this expression. But if f is not quadratic, then this result does not hold. So you still have to pick alpha k equals to argmin of this method. But the conjugate direction method, you can try to do the following. In the case of nonlinear f, then you pick beta k equals to okay, you take the, so beta k is computed in a slightly different fashion, and alpha k equals to argmin of a this is one way to compute Q conjugate vectors. I mean, there is no Q function now, but anyways, this is the way to generate the direction by changing the value of beta k slightly. And then alpha k is still computed using argmin. Now remember, if f was quadratic, I could compute alpha k exactly. But if f is nonlinear, then you cannot really do this argmin that easily. So you will do inexact minimization. So by inexact minimization, what I mean is you will sample alpha over the line, and then you will pick the best alpha, or alternatively, you can have a smaller optimization problem, gradient descent problem for finding alpha, which you will terminate at some point of time, maybe after 100 iterations, maybe after 50 iterations, and so on. So you will do an inexact minimization to find alpha k. Okay, so dk you can still find using the method, but alpha k is something where you will have to solve some optimization problem to solve this problem approximately, pick an alpha k, and then proceed with the next round of iteration. So people in electrical engineering, especially people who go to computational electromagnetics, they tend to do this kind of simulation, and therefore they need to solve this kind of problem using conjugate direction method. Okay. So that completes conjugate direction method. In the next class, which will be next Monday, I will talk about quasi-Newton method. So the idea behind quasi-Newton method is very simple. I am computing the gradient. So let me give you some idea about any questions on this before I jump on to quasi-Newton? No, right? Let me use this side. So Monday will be discussion on quasi-Newton method. So what is quasi-Newton? So remember Newton's method, we need second derivative inverse. Okay. So quasi-Newton says that look, we are computing the gradient anyways. What's second derivative of a function? What is fx? This is basically I don't want to. Okay, let's pick it. Let's say x is in R. Okay, so what is d2f over dx square? It's df over dx x plus h minus df over dxx over h limit h goes to 0. Right? This is what the second derivative of a function looks like. I seem to be computing this already, right? So I have the first derivative of the function at x naught. I have the first derivative of the function at x1. Okay. So can I use this operation to compute the second derivative? What would be the inverse of second derivative? That would be limit h goes to 0, h over this whole thing. That's my second derivative inverse. So if I'm picking h, my step size is small, so my alpha k is small, so which means that I can use this method to compute an approximation. By the way, this is, of course, this is an equality, but let's say I remove this limit h goes to 0, then I have an approximation. It's no longer an equality, but my h is small, right? So I know that my second derivative inverse is approximately equal to this value. So as long as this value is greater than 0, it's positive definite, I can use this for running my gradient descent algorithm, right? So I'm doing more from less. So all I'm doing is computing the gradients, and knowing this identity, I'm exploiting this identity to get an approximation of the second derivative inverse and use that for solving the optimization problem. So I'm not computing second derivative at all, right? I'm just using derivatives to get an approximation. So that's the idea behind quasi-Newton method. How can I do more from less? How can I just compute the derivatives and somehow magically compute the second derivative inverse and use that for running my algorithm? So we'll study that next week on Monday. Thank you.